Okay, now we're going to try to kind of do the same argument, but we're going to do it for infinite sets. So here's our table, okay? And notice that there is no nth row. I mean, it just goes on forever, okay? So I have x1, x2, x3, dot, 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 right? And s1, s2, s3. So what I want to show is that if S is equal to the set x1, x2, x3, dot, 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 so this is an infinite set, okay? Then the cardinality of the power set is still larger than the cardinality of S, right? This is what we want to show, okay? So we're gonna do the same argument we just did. We'll take the same definition of S prime, right? S prime is the set of all x sub I, right? Such that x sub I is in S. That means that S prime is the subset of S because all of its elements come from S, and x sub I does not belong to S sub I, okay? So S prime is not here, okay? But S prime should be in the power set of S, okay? So let's see. I mean, it's definitely a subset, like we said, okay? And if I look at S sub I can't be equal to S prime because X sub I belongs to one of the two sets, but not both, right? So they have to be different, right? So wow, this argument really does extend to infinite sets, and the conclusion is that the power set of the, let's say the natural numbers, okay, its cardinality has to be greater than the cardinality of n, okay? That's quite surprising, right? Because what's the cardinality of n? It's an infinite number, right? And what we're saying is that we found something that's larger. That's, I don't know, if that doesn't surprise you, I mean, I think it should. I find it very surprising, okay? So yeah, we have infinite sets that have different cardinality, okay? What does it mean for two infinite sets to have the same cardinality? Well, it just means that I can line them up in a row like we did in the previous slide, right? If I can line things up in a table where I have an element of one, an element of the other, element of one, element of the other, if I can do that, then sure, that means that they have the same cardinality. If I can't do that, then no, they don't have the same cardinality, okay? So here are some kind of famous infinite sets, okay? So kind of our main infinite set is right here, right? This is the positive integers. 1, 2, 3, 4, 5, 6, okay? We use those to count, right? And so these are kind of the counting numbers, okay? And the cardinality we actually say is countable, okay? And that's the phrase we're going to use to mean that it has the same cardinality as the counting numbers, means that it's countable, okay? So here's the easiest countable set, and that is the natural numbers, 0, 1, 2, 3, 4, right? The counting numbers are 1, 2, 3, 4. This one just has 0 in the front. And as you can see, I can actually set them up in rows. So 1, 0, 2, 1, 3, 2, 4, 3, and so on, right? I can just put them in a table with an element of one, an element of the other, and just keep going down. So yes, they have the same cardinality, okay? Perhaps more surprising, all the integers actually has the same cardinality as the positive integers, right? And the reason is that I can line up all the integers in a table, right? With one row for each element of the integers and one row for each element of the counting numbers or the positive integers. And here's the trick. The trick is I put 0, right? Let's just start with that. And then we'll put 1, right? But 1 minus 1, okay? And then we'll put 2, right? But again, 2 minus 2. And then we'll put 3, but again, that's going to be 3 and minus 3, and so on, right? So as you can see, I'm actually writing down all of the integers, right? But I'm able to write them in such a way that they line up in rows very nicely with the positive integers, okay? Now, even more surprising than that, the rational numbers are also countable. And this is kind of an interesting trick. So the way to kind of see it is to, again, see it in groups. So I'm going to group them like this, okay? And what I want you to observe is that in this set, they all add up to 1, okay? And what I mean is the numerator and the denominator, if I add those, I get 1. And then here, they add up to 2. In here, they add up to 3, and so on, okay? So now you see how it is that I'm writing the rational numbers one after the other, okay? So, and this is actually all of the rational numbers, because what are the rational numbers? we have a numerator, which could be, these are the positive rationals, right? So we have a numerator, which is kind of a positive integer, and we have a denominator, right, which is a positive integer. Okay, I throw in 0 as well, just because, right? So technically, this is not q plus. This is actually q greater than or equal to 0. Okay, but it doesn't much matter. Okay, so how can I add up to 1? Well, there's only one way. It has to be 0 and 1, right? And remember that the second number can't be 0, so that really is the only answer, right? Now, how can I add up to 2? Well, I can have 0 and 2, 1 and 1. I can't have 2 and 0 because the second number can be 0, so those are all of the ones that add up to 2. How can I add up to 3? 0 and 3, 1 and 2, 2 and 1. Again, no 3 and 0, okay? So if I have two numbers, p and q, right, if I add them up, p plus q, well, that's eventually going to come up in this list, right? And when it comes up in this list, I will see p and q together, okay? So this really does enumerate all of the rational, non-negative rationals. And yeah, it puts them in a table together with the counting numbers 1, 2, 3, 4, 5. So they really are countable, okay? How about all the rationals, not just the non-negative ones? Well, I think by now you kind of expect a trick, which is that I'm going to do the exact same enumeration I did before, except I'm going to alternate signs, right? For the positive and negative of each one of the previous row. So I will actually get all of the rationals. So all of these sets are actually countable. They have the same cardinality as the counting numbers or the positive integers. Are there some sets that I can't do that with, some infinite sets? Yes, we already know one, right? The power set of the natural numbers that has a larger cardinality, because the power set of anything has a larger cardinality than the natural numbers. So it's larger cardinality than n. That means I can't put it in this table, okay? This is really, really surprising stuff, okay? So let's talk about some uncountable sets. Like I said, we already know the power set of n, right? But I'm going to try to use that to find another one. So here's what I'll do. Do you remember how we use bits to represent our choices for power sets? So if I had 3 elements, then I would use 3 bits. And each bit would tell me whether I would include that element or not in a specific subset. Okay. So can we do that to n? Okay. And I'm sure we can, right? So what we would end up with is kind of numbers, right, that look like this, right? So this says no for the first one, no for the second one, but yes for the third, no for the fourth, yes for the fifth, and so on. That's not a number, right? Because of the dots. Our numbers actually end after a certain number of digits. So this doesn't work, right? That is not a number, and that's actually a good thing, because if it was, then we'd go back to having the same cardinality as the counting numbers, which you already know is not the case. Okay, so here's the trick though. I'll take that string of numbers, right, and I'll put a decimal point. So this is 0 point something, right? And now all of a sudden that actually is one of the numbers that we know and love, right? 0 point and then a bunch of zeros and ones. That actually is a number. In fact, it's a number between 0 and 1. Okay, so what have we just shown? Really what we've shown is that if you look at the cardinality of the numbers between 0 and 1, that actually is the same as the cardinality of the power set of n. So the cardinality of the numbers between 0 and 1, sorry, let me write that correctly. Okay, so if I have the numbers between 0 and 1, that's a set, okay, it's an interval. And if I take that cardinality, that is actually the same as the cardinality of the power set of n, right? Which we already know is bigger than the cardinality of n. Okay, so that's surprising, right, in its own right. And actually, I'm going to say something even stronger. The cardinality of r is equal to the cardinality of the numbers between 0 and 1, right? And that's simply true because I can multiply r by some scaling factor. Or rather, I can multiply 0, 1 by some scaling factor and get arbitrarily larger and larger intervals. Okay, so yeah, that does hold. Okay, so let's summarize what we're seeing here. And cardinality of r is greater than the cardinality of n, right? Who would have thought, right? I mean, this is insane. I mean, we're having infinite sets that are bigger than other infinite sets. We have some infinite sets that have the same cardinality but are very, very different looking. By the way, we have infinite sets that have the same cardinality as proper subsets of themselves, right? That's actually a characterization of infinite sets. All infinite sets do that. So and no finite set can do that. So that's one of the ways that you could define what it means to be infinite. Okay. Now all of this stuff, like I said, it's it seems crazy. Okay, and it all comes from one guy, and that's George Cantor. Okay, and Cantor is the one that discovered that there was more than one kind of infinity. And the argument that we used is due to Cantor, and it goes by the name diagonalization. Okay, so this is the x sub I does not belong to s sub I argument. Okay, and it's called diagonalization because you can think of the diagonal, which is all of the entries that have the same index, right? So x sub I does not belong to s sub I, the same index. Okay, so anyway, George Cantor kind of built this notion for us. Mathematicians have referred to it as a paradise, right? Although it's sad to say that his contemporaries didn't feel the same way, and they weren't quite sure that what he was doing actually made any sense. Very sad to say. Cantor died not knowing that what he had done would actually become accepted by the mathematical mainstream and just become part of this wonderful, wonderful thing that we know of as sets. Okay. So anyway, I wanted to show you the Cantor's paradise. We're not actually going to do that much more of it because we're interested in discrete structures, which mostly are finite. They're especially finite when we're talking about computers, right? If I'm going to represent it inside of a computer, finite is a good thing. But here we are. We're talking about sets. We just have to talk about Cantor and diagonalization.